In this video, we'll talk about some more of the experiments that showed the dual particle and wave nature of light and matter. The first one we'll talk about is the photoelectric. So the photoelectro effect was observed in the early 1900s. What was done in this experiment is light was shined at a metal surface, and when the light hit the surface, we could measure one electron being ejected. So this was already consistent with the idea of the particle nature of light, where if we have one photon, we could get one electron off the surface. But this also helped to show that the different photons had different energies. So if we shine red light on gold metal with a low frequency, it was observed that no matter how intense the light source was, so whether it was dim red light or bright red light, we couldn't eject a single electron from the surface of gold metal. However, if we used a blue light, which has a higher frequency and so a higher energy, we can get an electron ejected from the surface of the metal. And this would be true even with dim blue light, showing that in order to generate the photoelectric effect, you just needed to have a photon with high enough energy to ionize the metal. And if the photons, like the red light, didn't have enough energy, no amount of them would be sufficient to eject an electron. In other words, in order to eject one, you're going to need photons with a frequency above a certain threshold. And more specifically, the energy of that given photon must be higher than the binding energy of that electron to the metal. Furthermore, the kinetic energy of the ejected electron, so once we eject electron from the surface of the metal, the amount of energy that electron will have will be the energy of the incoming photon minus the binding energy. So if a blue photon has enough energy to eject an electron, a violet photon would not only be able to eject that electron, but would cause that electron to leave the surface of the metal with a higher kinetic energy. And since this energy is related to the constant times the frequency, we can rewrite this showing the frequency of the photon and the frequency of the lowest possible energy photon to cause an ejection. So again, we have the photon energy and the binding energy with this minimum frequency needed. So let's try and practice this. So if, for example, we have a green light that's capable of the photoelectric effect from the surface of a metal, we can ask, will a violet light be able to eject photoelectrons from the same metal? And the answer to this is yes, it will. So violet light with a shorter wavelength is going to be a higher energy. And so if green light can eject a photoelectron, violet light should be able to as well. We can do another practice problem here. So let's say we know the energy required to remove an electron from the surface of rubidium, and this is 208.4 kilojoules per mole. We're going to irradiate this with 254 nanometer light and find the maximum kinetic energy that every released electron can have. And so we have our kinetic energy is equal to the energy of the photon minus the energy required. So we can rewrite this, so we know that the Ke is going to be equal to hc over lambda. And notice this is in kilojoules per mole, so if we just wanted individual kilojoules, we're going to have to divide this. So this is going to be 208.4 kilojoules per mole. And we have to convert this to individual photons and individual joules. So plugging this in, we get the Ke is equal to 6.626 times 10 to the negative 34th joules times seconds times the speed of light, meters per second, divided by the wavelength. But we have to remember to put that in meters. And setting up our energy required to eject it, so 208.4 kilojoules per mole, and that's 1,000 joules per kilojoule, and Avogadro's number of photons per mole. Plugging the pieces of these, we get the kinetic energy is equal to 7.83 times 10 to the negative 19th joules minus 3.46 times 10 to the negative 19 joules. We get the kinetic energy of a single electron ejected from the rubidium with this ultraviolet light would be 4.36 times 10 to the negative 19th. So Einstein explained this photoelectric effect in 1905. And again, this provided further evidence that photons behave both as waves and particles. And this is part of why he won the Nobel Prize in Physics in 1921. This picture here of Einstein on the beach was actually taken here in Santa Barbara, California, about 10 years after he won his Nobel Prize. So he had a few experiments that established that light is both a particle and a wave. It turns out that actually all matter has particle and wave-like properties. And this is described by the de Broglie equation, where the wavelength of matter is equal to Planck's constant divided by its mass times its velocity. So this means that any moving particle, so anything with mass and a velocity, also has a wavelength. The reason that we don't observe the wave-like properties of most matter is that for large objects, this wavelength isn't going to be observable. Because if the mass is very large, that means this wavelength is going to be relatively very small, and quite possibly so small that it's impossible to measure. But for something like an electron, which is still a fundamental particle and has a mass, but it's a very small mass, it is indeed observable. So let's look at a couple examples using that equation. First, let's calculate the wavelength of a tennis ball moving at 44.7 meters per second. So to do this, we have the wavelength is equal to 6.626 times 10 to the negative 34th. And we have a mass of 47 grams. Remember, though, that the units of joules are kilogram meters squared per second squared, so we have to convert this to kilograms. And then we have its speed. And plugging all this in, we get that the wavelength is 3.15 times 10 to the negative 34th meters. So you'll note that this is smaller than even the smallest gamma ray. And so this isn't really something that we could measure or observe. Now, if we look at the wavelength of an electron, which has a much smaller mass, and we use the same equation and a much higher velocity, we get that the wavelength of an electron traveling at the speed is about 7.27 times 10 to the negative 11th meters, which is definitely in the range of some of the higher energy types of light. If we compare this to a radius of a hydrogen atom, you can see a hydrogen atom is about 5.29 times 10 to the negative 11th meters. And so this is something that we could actually experiment and test and observe. And generally speaking, if a wavelength and particle size are similar, we have to consider both the wave and the particle properties. We can consider some of the other properties of waves that we can see with light, for example. And one of these would be constructive interference. So if you have two waves in phase, so they go up and down at the same time, and you combine them, you get a wave of a stronger amplitude. If they're out of phase and you combine them, then they'll cancel each other out, and you'll actually observe nothing. So if we do this with a light wave, and we shine light through two really small slits, these waves will overlap, and we'll actually see an interference pattern where the light will be brightest, where the overlapping light waves will have constructive interference, and we'll see these dark spots where the overlapping light waves will have destructive interference. So we can try this double slit experiment with maybe something else that has an observable wavelength. If we had something with just two slits that was matter instead of a regular wave, so like say a bunch of marbles through holes just big enough for the marbles to go through. And so if we just took some particle and measured where it hit going through tiny slits, we'd see that they just stack up exactly on the other end of the hole. And so just like the way we can't observe the wave nature of something like a tennis ball, if we had some large particle with slits just big enough for it to go through, we won't observe any interference. However, we can do this experiment with electrons, and if you pass electrons through a double slit just big enough for an electron to pass through, instead of seeing just two bands of electrons, you'll actually see a pattern of high frequency and zero frequency impacts besides those two columns coming from the destructive and constructive interference due to the wave-like nature of the electron. So with electrons, we can observe this interference pattern. And so in conclusion, we can actually observe the wave-like nature of individual electrons.